the previous lecture, we were describing general structure of an optimization algorithm to solve an unconstrained optimization problem. We ended up the last lecture by mentioning that we need a line search method to find the step length to move on from the current iterate xk to the next point xk plus 1. Now in this lecture we will discuss a few inexact line search methods to find this step length. Needly, in this lecture, we will consider to discuss four inexact line search methods. Those are Armijo together with a backtracking rule. Next, Armijo-Goldstein rule. Thereafter, the Wolf rule or the Wolf-Powell rule. And finally, the strong Wolf-Powell rule will be described. In the previous lecture, we were describing the general structure of a general descent algorithm, where after describing the general structure of a descent algorithm, we also have got to know a few terminologies. Those are descent property, quadratic termination property, global convergence, and local convergence. Towards the end of the previous lecture, we were discussing how to find step length to move from a point xk to the point xk plus 1. To find a step length from the point xk along a descent direction dk, a common perception is that as we are trying to minimize the function, we can go for taking a step length along the direction dk as long as the function value gets a smaller and smaller value. So we take a step, say alpha k, that gives us the minimum most value of the function along the direction dk. So alpha k is chosen to be argument of the minimum value of the function f at the point xk along the direction dk. If we are choosing alpha k by this equation, we name such an alpha k as an exact step because we are trying to minimize the function along the direction dk and trying to obtain a minimum point, an exact minimum point of the function f along the direction dk. However, we note that to evaluate an exact step size alpha k, we may require solving a nonlinear equation of function of one variable given by phi dash alpha is equal to 0, where phi alpha is this function. As this is a nonlinear equation of one variable, commonly we need to employ root finding method for functions of one variable. And hence, to identify an exact value of alpha k, we may require too many evaluations of function values together with possibly values of the derivative of the function phi. And these altogether makes computational cost of exact line search really very high. So practically what we do, we use a moderate step length that satisfies an adequate decrease of the function value. By this moderate step length, we mean a step that is not too short and not too large. In fact, we need to employ moderate step length because too short or too large step length may lead non-convergence optimization algorithm. We will see such examples very soon. Before that, let me tell you that the motivation behind inexact line search is not only to avoid excessive computational cost of exact line search, but also the following three facts. That the first point, that when we endeavor for an exact minimum, we first have to assure that there exists an exact minimum of the function f along the direction dk, and this might not always be the case. For example, consider minimizing the function e to the power say minus alpha over alpha greater than 0. For this function, we notice that there is no minimum of the function e to the power minus alpha for alpha greater than 0. We have the graph of the function like this, where x-axis or alpha axis is an asymptote and hence the function do not have any exact minimum for alpha greater than 0. The next motivating point is that a descent algorithm may not converge to a minimum if the step length is chosen to be very small. A descent algorithm, by descent algorithm we mean at consecutive points the function values are degrading. That means f at xk plus 1 is less than f at xk for every k. A descent algorithm may not converge if the step length is too short. For example, let us consider the function if x is equal to x square, a function of one variable. Choose the initial point to be x naught is equal to 2, and for this function a descent direction at the initial point x naught is the direction of the negative x-axis. Here the graph of the function is this parabola. We are starting the iteration at the point x naught is equal to 2. At x naught we notice that the descent direction is along the negative x-axis. So we take d naught is equal to -1. Now by taking the step length across iterations as alpha k is equal to 1 by 2 to the power k plus 1, we see that we are progressing towards x naught, then x1, then so on towards the value 1. At each and every point of this x naught, x1, x2 and so on, the descent direction is dk is equal to -1. In fact, you could choose any negative value here instead of -1, but we are just choosing here dk to be -1, and by choosing this dk is equal to -1, which is a descent direction, and alpha k to be 1 by 2 to the power k plus 1, we see that the function value at xk plus alpha k dk will certainly degrade. That means function value at xk plus alpha k dk is less than the function value at xk. Let me give you a home task here. You please verify that this inequality is true. Together with this inequality, you also please verify that the sequence xk is given by xk is equal to 1 plus 1 by 2 to the power k. And hence we see that this xk converges to the point 1, which is not a local minimum of the function fx equals to x square. And hence a descent algorithm, an iterative process with a descent direction, may not converge to a minimum if the step length is too short. Here notice that as k progresses, the value of alpha k gets very small and small values. And due to this, although the function value across the consecutive iterations gets degraded, but when xk reaches to the point 1, the function value gets stuck at the point when xk is going to converge the point 1. And hence we should not go with too short step length, otherwise a descent algorithm may not converge. Now I will next show an example where we will see that a descent algorithm may not converge to a minimum if there is no significant decrease of the function value in the consecutive iterations. The third point is that a descent algorithm may not converge to a minimum if there is no significant decrease of the function value across the consecutive steps. Even if we take steps that are of substantial length. By steps we mean the step lengths. For example, we consider if x is equal to x square, a function of one variable, choose the initial point is equal to 2, step length alpha k, as 2 plus 3 divided by 2 to the power k plus 1. And with this step length, if we look at the graph of the function fx equals to x square, we can find that on the graph of the function y is equal to x square, at the point 2, the initial point, a descent direction is along the negative alpha axis. Now, by taking the step as alpha naught is equals to 2 plus 3 by 2, we are at the point minus 3 by 2. At minus 3 by 2, a descent direction is along the positive alpha axis. Then again we reach at the point here by taking the step length alpha 1 is equal to 2 plus 3 by 2 square. We are at the point 5 by 4. At 5 by 4, a descent direction is along the negative alpha. And in general, we can find that at the iterate xk, a descent direction is given by dk is equal to minus 1 to the power k for every k starting from 0, 1, 2 and so on. Here for this function, with these choices of alpha k, dk and x naught, we see that at the initial stage, the function value degrades from this point to this point. Then next iterative point gives us a degradation of function value here. Then as the iteration counter k increases, the function value eventually gets stuck at the value y is equal to 1. When k value gets larger and larger, we'll find that the iterative point xk eventually fluctuates between 1 and minus 1, taking up the function value almost is equal to 1. And this scene is happening due to the fact that the difference between the function value at xk plus 1, that is xk plus alpha k dk minus f of xk, these value you can compute and find that is given by 1 by 2 to the power k plus 1 times 2 plus 3 divided by 2 to the power k plus 1, which is very small when k is larger and larger. So here I give you some home task that you prove the first if xk plus 1 is less than if xk by showing that the difference between fxk plus 1 and fxk is this expression, which is obviously negative, and also identify the expression for the sequence xk and show that the sequence xk is a divergent sequence. And therefore in this example, although we have taken substantial step length, but as there is no significant decrease of the function value across the consecutive iterates, the sequence xk generated by this descent iterative process does not converge. In fact, in this example, there is also a problem that we have taken the step length too large. So from these three observations, we get an immediate feedback that we should not employ the step length alpha k very short or very large or aggressive, and also we need to confirm that across the consecutive iterates there is a significant decrease of the function value. In the next, we shall describe four rules that are generally acceptable set of conditions for choosing alpha k, moderate alpha k, which although inexact values of local minimum but give global convergence of any descent algorithm. This word descent algorithm I will quite often use. By the descent algorithm, we mean that we are approaching with a descent direction dk at each and every iterate xk, and hence across the iterations in the consecutive steps the function values will get degraded. Now in the four rules that I shall describe below, which we shall refer as inexact line search rules. We take a standing assumption that the objective function, is continuously differentiable. That is, if we have a function of several variables, say f depending on n variables real valued, which is the objective function, and here we are endeavoring minimization of this function f, and unconstrained minimization. We assume that this function f is having continuous first order partial derivatives, which we denote by f belongs to C1, and therefore for any given xk and a direction dk, the function phi given by fxk plus alpha dk is also a continuously differentiable function. Here we notice that this function phi is a function of one variable alpha. The first inexact line search rule that I would like to describe is the Army-Joe condition, or sometimes people spell out Army-Ho condition together with a backtracking rule. Army-Joe condition is such a condition that ensures a sufficient decrease of the objective function value. What it suggests is the following, that let us suppose the graph of the function phi on the plane of alpha and y is, say, this graph, y is equal to phi alpha. Now at the point xk we have alpha value is equal to 0, and hence the function value is given by phi 0. By function value we mean value of the objective function f. This is the line of y is equal to phi 0. As the function f is assumed to be continuously differentiable, there is a tangent at each and every point on the graph of the function y equals to phi alpha. The tangent at alpha is equal to 0 is given by this line. The equation of this line, tangent at alpha is equal to 0, is given by y is equal to phi 0 plus alpha times phi dash 0. Armature rule suggests us that you consider a line passing through this point 0 phi 0, and that lies in between this line y is equal to phi 0 and this tangent line. So we consider a line, say this line, and then in order to ensure a sufficient decrease of the function value, you consider those points alphas for which the function values are lying below this line. That means you choose those alpha values for which phi alpha is lesser than or equals to the function values at the expression of this line, that is, say, given by y is equal to phi 0 plus a line in between this tangent line and y is equal to phi 0 is given by some constant multiplication C1 times alpha into phi dash 0, where the C1 lies in between 0 and 1. So you choose those alpha values for which phi alpha is less than or equal to phi 0 plus C1 times alpha times phi dash 0. From this graph y equals to phi alpha, we see that acceptable alpha values which are satisfying this inequality are set of all points from here to this, then from here to this point. So we get the range of alpha from 0 to this point, and then from this point to this point. So the union of these two intervals gives us acceptable alpha values for which the Armijo condition is satisfied. Acceptable alpha satisfying or Armijo condition. This inequality is referred as Armijo condition. So the Armijo rule states that to make sufficient decrease of the objective function, we need to apply a rule like this inequality with the value of C1 lying in between 0 and 1. A common choice of the C1 value is a value in between, say, 1/4 to half. We restrict the value of C1 lesser than equals to half because this Armijo condition is satisfied by a quadratic expression of phi. That means if you take phi alpha is equal to some positive value a times alpha square plus b alpha plus c, then you will find that with this quadratic expression for the function phi, the Armijo condition is satisfied only when C1 is chosen to be less than half, and therefore we commonly restrict C1 to be lying below half. Now we notice that this condition alone cannot restrict the alpha k value to be too small. Here we notice that if we choose alpha k very close to 0, those alpha k values are also satisfying this Armijo condition. But we really bother when alpha k value is very small. We should not choose alpha k value too small. And thus, to choose a moderate value of alpha, what we do? We give an initial estimate of the step length, the alpha value, that is a significantly large value. Say we start the process with an estimate of alpha value that satisfies the Armijo rule, say this, and then we backtrack this alpha value by a fraction multiple of this much amount of alpha, by a fraction multiple, let's suppose a tau multiple of this much estimated value, say alpha bar. So we get the point tau times alpha bar, say this point. Here we choose tau to be a fraction lying in between 0 and 1. We get the location of tau alpha bar is somewhere, let's suppose here, and then check at this point whether this tau alpha bar satisfies the Armijo condition. If not, then again you backtrack by a fraction multiple of this tau alpha bar. So we get tau square alpha bar, let's suppose somewhere over here, and we notice that at this tau square alpha bar the Armijo condition is satisfied. This entire process that start with an initial estimate of step length, say alpha bar, a significantly large value, then you backtrack this alpha bar value by fraction multiples, that tau alpha bar, tau square alpha bar, tau cube alpha bar, and so on. You keep considering this tau multiple of the previous step length and go for checking whether this a fraction multiple of alpha bar satisfies this Armijo condition or not. Once you identify a fraction tau to the power p for which tau to the power p alpha bar satisfies this Armijo condition, we stop this backtracking and we notice that this tau to the power p times alpha bar is a significant value of alpha that satisfies the Armijo rule. So in practice, we employ Armijo condition with this backtracking rule to find a moderate step length that gives us a sufficient decrease of the objective function value. Let me write this backtracking rule very neatly. We start the process with an initial estimate of the step length say alpha bar, which we choose a bit significantly larger and provide a fraction to backtrack, say tau, that lies in between 0 and 1. Then backtracking checks over a sequence of values for the step length. Those are alpha bar, tau times alpha bar, tau square times alpha bar, tau cube times alpha bar, and so on until we get an alpha value given by tau to the power p alpha bar for some natural number p that satisfy the Armijo rule. In order to accomplish this checking over the sequence alpha bar, tau square alpha bar, and so on, we can go for applying a while loop that you start initializing the step length alpha to be alpha bar and run a while loop that while phi alpha is bigger than phi 0 plus alpha times C1 phi dash 0, we reduce the alpha value by a tau factor. And when you will get out from this while loop, you will find an alpha that satisfies the Armijo rule. So you return that alpha when you get out from this while loop. Now here commonly in practice we choose the value of tau in between half and say 1/10. And also a common choice of the initial step length alpha bar and initial estimate is an unit step. You know the introductory article that introduces this Armijo rule is the article written by Larry Armijo entitled Minimization of Functions Having Lipschitz Continuous First Partial Derivatives, which came out from Pacific Journal of Mathematics in the year of 1966 in its 16th volume. Now here in this Armijo backtracking rule, we notice that we need to employ a backtracking rule to ensure a significant step length. Instead of this backtracking, Goldstein suggested us to choose a step length alpha k that is above a given line passing through the point 0, 5, 0. For example, let us suppose the graph of the function y is equal to phi alpha on the alpha y plane is, let's suppose, somewhat like say this one, y is equal to phi alpha. This is the line of y is equal to phi 0. The line that we have taken in the Armijo rule is say this line, which is given by the expression y is equal to phi 0 plus C1 times alpha times phi dash 0. But we have seen in the Armijo rule that if we go for employing alpha values which are giving us function value of y equals to phi alpha below this pink line, then we may have the cases where the step lengths are too short. To avoid this too short step length, what we do? We consider another line passing through 0, phi 0 so that that line lies in between the tangent and the line of the Armijo rule. So we consider a line, for example, say this line whose expression is given by y is equal to phi 0 plus alpha times phi dash 0 times some constant, let's suppose C2, which must be bigger than C1, then only this line will come below this line. As commonly we choose C1 to be below half, so here we can go with 1 minus C1, and this 1 minus C1 is certainly then bigger than C1, so this line will then come below this line. In order to avoid short step lengths, the Goldstein rule suggested that you take those alpha values for which the graph of the function y is equal to phi alpha is above this line, and accordingly we will get the set of alpha values which are giving us function value bigger than function value above this line is alpha starting from here and any value bigger than this particular point. So in order to avoid short step length, you consider a restriction of phi alpha to be bigger than this expression, and in order to consider a significant decrease of the function value, you also put a restriction that phi alpha should be smaller than this expression. And accordingly, these two restrictions will identify the set of alpha values in between from here to this point and then from here to this point. So these range from here to here, union from here to here are set of acceptable points. Those are satisfying both these restrictions, that above this line and below this line. We now neatly write this next rule, that is Armijo-Goldstein rule, which we consider here inexact line search 2, which says that instead of backtracking we can take the following condition to avoid small step size, that you fix up some value of C1 in between 0 and half and then choose alpha k value that satisfies both of Armijo condition given by phi alpha less than equal to phi 0 plus alpha C1 phi dash 0 and the Goldstein rule that phi alpha is greater than equals to phi 0 plus alpha times 1 minus C1 times phi dash 0. You know, the introductory article that introduces this condition is the article by Goldstein entitled On Steepest Descent that came out through Siam Journal of Control. If you are interested, you may visit this particular paper to know more about the Goldstein rule. Now here we notice that instead of considering this particular rule, the Goldstein rule, to avoid short step length, we could have also considered a similar rule, that you choose a value of C2 instead of 1 minus C1, and that C2 must lie in between half and 1. Then we notice that this Goldstein condition is equivalent to phi alpha minus phi 0 divided by alpha bigger than or equals to C2 times phi dash 0. Now by Lagrange's mean value theorem, this inequality can equivalently be written as phi dash of some xi, where this xi lies in between 0 and alpha. This phi dash xi is bigger than or equals to C2 times phi dash 0, which is closely related with phi dash alpha bigger than or equals to C2 times phi dash 0. This inequation, we notice that, confirms that the rate of increase of the function phi is at least this much amount. As the rate of increase of a function gives us a bending information, We commonly refer this condition as the curvature condition. Now you notice that as the condition 2 is closely related with this condition, we can replace this condition 2 by this condition to ensure not too short step length. In fact, use of this condition gives us a side benefit. The side benefit is as follows, that the condition that if we take alpha k value that satisfies phi dash alpha greater than equals to C2 times phi dash 0, then we have phi dash alpha k greater than equals to C2 times phi dash 0, which further gives gradient of f at xk plus alpha k dk transpose dk greater than equals to C2 times gradient of fxk transpose dk. And hence by subtracting on both the sides by gradient of fxk transpose dk, we get gradient of fxk plus 1 minus gradient of fxk whole transpose dk is greater than equals to C2 minus 1 times grad fxk transpose dk. Here this xk plus 1 is this expression, the next iterate from the point xk. We see that this expression on the right, this expression is a positive quantity because C2 is less than 1 and dk is a descent direction of the function f at the point xk. And hence what we get here is yk transpose sk is greater than 0, where yk is the vector difference of the gradient of the function f xk plus 1 and at the point xk. And sk, this vector is the difference between xk plus 1 and xk. So if we employ this rule to choose the step length alpha k, then we get a benefit that yk transpose sk is greater than 0. And this condition yk transpose sk bigger than 0 makes a very popular quasi-Newton method, the BFGS method, well defined. We'll see later that this BFGS method, which is a quasi-Newton method, is well defined only when this yk transpose sk is greater than 0. So to make the popular BFGS method well defined, we can go for employing this rule, which possibly was first considered by a great optimizer, Wolf, and hence it is known as the Wolf rule. So in the next inexact line search rule, we consider the Armijo rule together with this Wolf rule. As these two conditions, Armijo rule together with Wolf rule, was also considered extensively by a great optimizer, Powell, we name this inexact line search 3 rule as the Wolf-Powell rule. That says us to fix some values of C1 and C2 that satisfies 0 less than C1 less than C2 less than 1 and choose the step length alpha k that satisfies the Armijo rule, that is phi alpha is less than equal to phi 0 plus C1 alpha into phi dash 0 together with the curvature condition that phi dash alpha is bigger than or equals to C2 times phi dash 0. Let us now figure out in a hypothetical figure for y equals to phi alpha. in which both these two conditions are satisfied. So let us suppose in the plane of alpha and y, the graph of the function is say somewhat like this. Y is equal to phi alpha. Here goes the line y is equal to phi 0, and let us suppose the line given by this expression in the Armature rule in this graph is say this line. Now for this condition, the curvature condition to be satisfied, we need to find out those alpha values at which the slope of the tangent on the graph y equals to phi alpha is bigger than this quantity c2 times phi dash 0. The slope of this pink line is c1 times phi dash 0. The slope of the tangent line is phi dash 0. As c2 is lying in between c1 and 1, so the slope of c2 times phi dash 0 is some slope somewhat, let's suppose like this. Now we consider to identify those values of alphas at which the tangent is having slope bigger than the slope of this line. We find out the points. Let's suppose at this point the tangent is parallel to this line, and here at this point also the tangent is having slope same to this line. Now notice that any point on the right of this point, at this point and all these points, the tangents are having slope bigger than this quantity. So till this point you consider, then next to this point we notice that the tangent is having slope smaller than this quantity, and hence the second condition identifies the range of alpha values lying in between from here to here, then from this point to the right of all these points, and hence the set of all alpha values which satisfy both these two conditions are the points from here to this point, then from here to this point. So these set of points of alpha values satisfies both the conditions 1 and 2 in the Wolf-Powell rule. You know the introductory article that introduces this Wolf rule is the article by Wolf entitled Convergence Condition of Ascent Methods. By ascent methods, we mean those methods for which across the consecutive iterates the function values are increasing. That means instead of fxk plus 1 less than fxk in descent methods, we consider this inequality to be greater than in ascent methods. This article came out through Siam Review in the year of 1969 in the 11th volume on the pages 226 to 235. Now in the Wolf rule, there is a bit problem that the points which are far away from the local minimum, like the point over here, they also satisfy this Wolf rule. In order to avoid choosing some alpha k that is far away from a local minimum, what we do? We make a safeguard that we consider the slope phi dash alpha to be lying in between minus epsilon to plus epsilon for some small value of epsilon. Then you notice that this condition, or in a compact way the condition phi dash alpha's absolute value is less than equal to epsilon, ensures that the step length alpha is very close to a local minimum or at least a stationary point. So instead of considering just this left hand side in the Wolf rule, we also consider a safeguard on the right hand side that you choose phi dash alpha to be less than equal to epsilon here you consider minus c2 times phi dash 0, and then we can ensure that the step length alpha k is not far away from a stationary point. This condition, absolute value of phi dash alpha less than equal to minus c2 phi dash 0, is called a strong wolf condition. So with this Armijo rule, the first one, and this condition, absolute value of phi dash alpha is less than minus c2 phi dash 0, gives us the next inexact rule, the inexact line search 4, which we name as strong wolf condition or strong wolf vowel condition, that tells us to choose alpha k that satisfies the Armijo condition that phi alpha is less than equal to phi 0 plus c1 times alpha times phi dash 0, and the strong wolf condition, absolute value of phi dash alpha is less than equal to minus c2 times phi dash 0 for some c1 c2 lying in between 0 and 1, and c2 is bigger than c1. Let us now try to figure out the set of alpha values which are satisfying both of these two conditions in a hypothetical graph of y is equal to phi alpha. Let's suppose the graph of y equals to phi alpha is a graph of, let's suppose, this type: y is equal to phi alpha. Here is the line y is equal to phi 0. Now we notice that the second condition essentially tells us that you figure out those values of alphas for which the graph of the function y equals to phi alpha is Lipschitz with this constant k is equal to minus c2 phi dash 0. So we consider two lines, one having slope c2 phi dash alpha and another having slope minus c2 times phi dash alpha. Now with these two crossed lines, you go for scanning the points on the graph of the function and check whether those points are such that in a neighborhood of that point, the graph lies in between this region, here and here. We notice that this particular point is not a point at which you have this condition satisfied. But we notice that when we are at this point where the tangent is parallel to this line, the graph of the function y equals to phi x is still not lying in between these two shaded portion, but immediately after this point we see that the graph of the function lies in between these two shaded points. So from here to till this point, you will find that the graph of the function lies inside this shaded region. So this is an interval of alpha values which satisfy the second condition. Similarly, you can also find set of all alpha values in between these 2 points also satisfy the second condition. So union of these two intervals will give us set of alpha values which satisfy the second condition, the strong wolf condition. Now we consider the set of all points that satisfy this first condition, then take the intersecting region which satisfy both the conditions. That will give us set of all points which satisfy both these two conditions. So here if we suppose the line given by the first condition is, let's suppose, this line, then the set of all points which satisfy both of these two conditions are from here to here and from here to say till this point. So this region and this region, union of these two alpha values are acceptable points which satisfy these strong Wolff-Powell conditions. Now, after the discussion of all these four inexact line search conditions, you may ask me a question that through a hypothetical graph, you have shown set of all possible values of alphas which satisfy the inexact line search condition 1, 2, 3, and 4. But is it always possible that there exists some range of alpha values for which this inexact line search condition 4 or the inexact line search condition 3, 2, 1 satisfied? For existence of step lengths satisfying each and every these inexact line search conditions, I would request you to visit two fabulous references written by one of the great optimizers, Roger Fletcher, and another book by Nocedal and Wright. If you are very much inclined on mathematics, or if you would like to take optimization as your research career, I would strongly suggest that you please visit the book by Roger Fletcher and by Nocedal and Wright. The book by Fletcher is similar to the book by Walter Rudin for mathematical analysis. As you might have already seen that the Rudin's book is such a book where the problems in the exercises are also concepts. Similarly, each and every sentence of this Fletcher's book is so precise that you will need quite a bit of time to understand those lines, but if you hang over a bit of time with the lines of the Fletcher's book, you will find that you are really enriched with learning optimization. Another elegant book on optimization in which you will find a detailed discussion on choosing step length is the book by Dimitri P. Bartsekas entitled Nonlinear Programming. You please look at pages from 34 to 39 of this Bartsekas book. You will find that not only exact line search, not only inexact line search, there are several other ways also to choose the step length alpha k. One of the most important ones is the diminishing step size, which tells us that you forget about all these exact and inexact rules. You just go to employ one sequence of real numbers alpha k that satisfies the conditions that it is not summable but it is square summable. That is, alpha k square is such a sequence that this series summation k equals to 1 to infinity alpha k square is convergent, but this sequence alpha k gives us a series which is divergent in nature. Or you take a sequence for which summation of alpha k is equal to positive infinity, but the sequence alpha k converges to 0. A trivial sequence that satisfies both of these two conditions, that either this or this, is the sequence 1 over k. With this choice of alpha k value which satisfies either this condition or this condition, which is known as diminishing condition, because of this condition alpha k tends to 0 is satisfied, we commonly get a global convergence of any descent algorithm that satisfies a few mild conditions. With this step size rule, this diminishing step size rule, descent is guaranteed only later when alpha k becomes small, and this condition summation alpha k is equal to positive infinity is imposed to guarantee that the progress does not become too slow. This diminishing step size rule has good theoretical guarantees. You please look at this Bartsekas book. You will find the theoretical guarantees. By theoretical guarantees, I mean the global convergence of descent algorithms. But often, this diminishing step size rule gives us a slow method. In the literature of identifying a step size rule, there is also a type of step size rule. Those are known as non-monotone line search rule. So far, in any of the step size rules, we were endeavoring to identify step sizes so that we get a guaranteed decency across the consecutive iterates. That means we endeavor choosing those alpha values for which we have this fxk plus 1 is less than fxk. There are certain step size rules which allow violating this condition that fxk plus 1 is less than fxk. That means at some iterates we allow increment of the function value, and by that we mean the line search is a non-monotone line search, and these non-monotone line searches can improve the likelihood of finding a global minimum, and also it can improve convergence speed in case where monotone scheme is forced to creep along the bottom of a narrow curved valley. For a reference of non-monotone line search, you may please visit an interesting article by Hagar and Zhang entitled A Non-Monotone Line Search and its Application to Unconstrained Optimization. In addition to this non-monotone line search, I also would like to suggest you to search recent inexact line search techniques by C and Sen, and also by Potra and C. With all these three references on modern techniques for inexact or non-monotone line searches, I stop this lecture here. In the next lecture, I will discuss global convergence of any descent algorithm that employs any of these four inexact line search methods that I have described in this lecture. Thank you. Thank you all for all of your kind attention.